Okay, so we saw an integer list, and now we want to build a list of arbitrary type, where by arbitrary type, I mean the list has only one type in it, but it doesn't have to be any specified type. We can make it a list of integers, a list of floats, a list of students, a list of points, a list of whatever we want. Okay, so to do that, we have to do a little bit of work, and we have to use some abstraction. And in this next few segments, I want to give you some ideas on how to do that, show you some code I wrote, some strategies you might want to pursue, but there are a lot of different solutions, a lot of ways to think about it. And I encourage you to explore and do whatever is comfortable for you. But let's look at some code and let me point out a few things. So I'll share my screen. Okay, so I organized the directory of some data structures that we'll be working on. You can see I have graph, hash table, list, queue, and stack. Let me look at the list data structure. And in here I have a make file. Hopefully you have seen make files before. If not, I'll give you a nice reference for how to build them. Just a nice way to be able to maintain your code. You can specify how the code's built, what the dependency graph looks like, and it ensures that when your executable is rebuilt, it satisfies all of the dependencies, but no more. So it's just a nice way of organizing your source code. And I have a test list source code file also. The way I do these things is I have the source code for the data structure, and then I have in a separate file a main function which tests the functionality in the source code file and verifies to the greatest extent possible that it's working as I expect. Okay, so I have a rule to make text test list, and I'll execute that rule via the make file. So make test list, and you see it knows automatically to invoke the client compiler where the include path is. It knows that you have to build list in order to build test list. It knows to create the object files, to invoke the linker, and to produce the executable. Okay, so if I run test list, you see it works, and you can imagine I've done a bunch of list manipulations there that I'm checking. And ideally, you would have an automated checks where you pass assertions that certain results are correct, but I'm not doing anything that formal in terms of software engineering, just showing you the way I've organized it. What I really want to do is I want to open up that test list file, and I want to show you from the user perspective what it looks like to use my list. And that will give you some hints about how to actually build your list. Then I'll look at the header file and maybe a little bit of source code, just enough to give you some ideas and get you going. Okay, so what does my test list file look like? So just to remind you, I am now the client who is using this generalized list that is your assignment to do. And I'm using it on a very simple example, similar to the one I've asked you to do on your assignment. I've defined a type called a pair, which is just two integers. And I'm going to create a list of pairs with this general list, okay? So a few things that I'm going to need for my list are special functions for how to handle certain aspects of this pair type, which my list, the way it's built, knows nothing about, right? It's not a list of anything in particular, so it needs some help. So it needs to know how to print a pair type. It needs to know how to free a pair type, right? Because if I try to destroy my list with a list destroy method, it might have several levels of mallocs within the struct type that I'm using within the list. And there's just no way that it can automatically free all of that in some recursive fashion. So you have to say how to free the type that you're putting in the list. And there could be other things you include, but that's all I'm doing here. I just have a function which creates a new instance of a pair, a very simple function. Okay, so it's very important to realize the importance of these two functions. It's the same thing as the qsort function. Qsort did not know, well, I should say the qsort function could sort anything, but in order to use it, the qsort function had to be told how to compare any two elements of the thing you wanted to sort. There's no way the author of qsort could have anticipated the things you're using it with and put in a comparison criterion themselves, right? So they supply the basic functionality and you pass in a pointer to a function, which does a little bit of the work. So that's the same thing with this list. You have to pass in a little bit of the functionality for it to know when you call list print, how to print It doesn't know how to print a pair without you telling it. And when you say list destroy or whatever function you want to have to free your list once it's finished, it has to know how to go through and free the data element by element of the list, because that's the idea of these functions. So what it looks like from the user perspective, I'm just going to create a list of these pairs and play around with it a little bit, use some functions. Okay, so the first thing I'm going to do is, there's no single way to do this, okay? This particular interface that I've created requires you to malloc list as the first step. So you have to create memory for the list. And then the list init function does not call malloc. So if you remember in the integer list example I did, there was a create list function which called malloc within the function. It's a question of style, who you want to handle memory allocation. As a general rule, it's good to not have memory allocation too deep in a sequence of function calls because it's easy to get lost. So you try to push memory allocation up as high as possible, but there's no firm rule. All right, so then the list init function is sort of like the constructor, and it takes the list which has already been allocated by the user, and this forces the user to see a little ugliness. All right, my goal with the integer list was to sort of completely hide everything from the user and just make it look like sort of a Python or a C++ data structure. So in list init, I give it the list pointer, and then I pass in these functions. Okay, so I'm giving it this is really a pointer to a function which says how to destroy a pair, pointer to a function, this last argument, which says how to print a pair. And then I had another function pointer, which I'll talk about later why we might use it, but which when you just use a list isn't used at all. And therefore I'm just going to pass null for that argument. That's a detail of my implementation, okay? So this is how you kind of create and configure a list of my abstract or my general type with these two methods, okay? Now I want to put some things in the list. So I first create a pair. So all new pair does is create an instance of a pair object or a pair struct, each of whose fields is one. So what I call them, X and Y, X is one and Y is one, okay? But notice it's a pointer, okay? So what I do is I put pointers in the list. So I have a list insert next function, and pay very close attention because this is not how you really typically want to present a list to a user. This is what I call the sort of order one interface. It's a low level interface. I'm going to show you a high level interface in a second, which I layer on top of this. But the list insert next function, which you can use, takes a pointer to the list, okay, which stores the root, as you can imagine. Null indicates that you want to insert this new element at the head. Otherwise, in place of null would be a pointer to the element after which you want to insert it, okay? And the element I want to insert is P. So I've said insert P at the head of the list, okay? And then I have the regular list print list function. Now notice list print, if you imagine what the source code looks like for the list, which I haven't showed you yet, the list print function obviously has to call the to str function, the pair to string function, right? So you can imagine somewhere in the source code for the list, there's a list print function, and it loops over each element of the list. And instead of calling print, it calls this function because it has a pointer to it because I passed in the pointer to the constructor, right? And so it calls the pair to string function, and it passes in the data that represents the arbitrary type. So it's of type void because it's whatever the list is made of. It doesn't have to specify at all. So in the function, you would cast it to, as we'll see in a second, type pair, and then you would just print each field of the pair. All right, we'll look at that in a second, but that's the spirit of it, just so there's no mystery. Okay, so this is a low-level interface because I have to keep around the element of where I want to insert, but you see then it's clearly an order constant time interface because this operation is independent of the length of the list, right? So people do their data structures that way because it exposes the complexity, the time complexity of the operations. List print is always going to be order n. Okay, so let's just use these order one, this constant time interface functions. See, to do it, you've got to expose them to them being the client, the user, me in this case, to a variable of pointer to list element. So I say, okay, starting with the list.head for I equals 1 to n, where n is the number of elements I want to put in, create a new pair. In the new pair, I just arbitrarily set some values, I integer divide 3, I mod 3. And then I say list insert next. So I want to insert this new pair p that you see I created right here with this constructor after the previous element. So I'm appending to the list, okay? But I always need to keep around the last list element in order to be able to call this list insert next, which is not a very high level function. So I have to say e equals e.next. So this isn't the kind of thing you typically want a user to see, but it's what they would have to if you were building a low level interface. And then I print the list as I continue to insert things. So you'd like to see the list grow, and the first time through until I is 3, it's going to be 0 here. And this is going to cycle from 0, 1, 2, and then back to 0 again. So that's what these represent, that I'm adding capital N of these pairs to the list until at some point I do something else, but I'm showing the list growing. All right, so you can imagine what my toString method looks like, but I'll show you in a second. Well, now I'm going to keep using the order 1 interface, and I'm going to remove an element of the list. Well, this list rem next function is saying, okay, I want to remove the head of the list, okay? But I always have to give it a pointer to the element prior to the one that I want to remove. That's the sense in which it's a constant time function. Otherwise, if I said remove the 23rd element, underneath the hood, the source code would have to go from the head of the list, find element 23, and then essentially insert that value in here, and then call list remove next. Well, then I have to pass it a pointer to the element that I want to remove, because I essentially want it to return, or to set for me, a pointer to the data that is in the list so I can free the data myself. I'll talk about that a little bit on the outside here. Since it's a very simple data structure, I can just call free. But I wouldn't worry about this detail quite yet, because I want to talk about the sort of first order aspects of the list. Then we'll get into that. And then I print the list. Okay, well now I want to think about the order n interface. So what would it look like if I didn't force a user to see that low level version of the code, but I wanted them to think more like in terms of indices and order n operations. So in that case, I have these other functions, list add, and list add allows me to specify an index, in this case index 3, and I'm going to add a new pair whose values are -1, 1 at index level 3. So you'll see that in the printout and the test code. Then I print the list, and then I call the element at function. Okay, so similarly I can say what is the element number 3 in the list, and notice it returns a pointer to a pair. It can't return a pair because I had to write the code entirely in terms of void pointers. So all the element at function knows how to do is return a void pointer, and I have to cast that pointer back to a pair if I want to treat it as a pair in my program. Okay, and then I print it with, I just use my handy pair to string function here, and so forth. Okay, so let me just look at a couple more aspects. This pair to string takes a pointer to a pair, right? But it's cast as a void pointer because that's required from the source code for the list. It can't specify a particular data type, but for a particular implementation of a list that I want to use, I can just cast it. Okay, so I say, well, this is a pair in this particular case, and this is how you print a pair. You just print it with brackets, and you print each element as an integer. Okay, so in the list source code, it calls this, it gets a string representation, and then it just prints that string representation to the terminal. Okay, and similarly, it says how to destroy an individual element of a pair. In this case, it's simple. I can just call free, but there might be much more complex structures. And then the new pair methods, which you imagine, it just creates an instance of a pair. Okay, so that's the client side view. I think the key thing here to understand is the difference between the low level interface that you might or might not choose to expose to the user, and the high-level interface, which seems a more natural way for a person to program, and you might layer one on top of the other. Okay, but I think it's important to think in terms of the low-level interface because the data structure is intimately tied to the time complexity of the operations that one performs on it. Okay, so the idea of an abstract data structure isn't particularly useful. It only makes sense in practice to use these things if they have guaranteed performance of certain canonical operations. Okay, so what I want to do next then, now that we've had a look at what this looks like from the client side, is I want to switch and look at the header file and how I formally define the interface.